Okay, so longitudinal waves, the particles move in the same direction that the wave propagates. So if our wave is going this way, it's going to cause our particles to move back and forth along parallel with the sound beam. So if I have, I know it's dark, you guys get this picture later, but it's my longitudinal wave. My wave is going that way. So my particles, they're going to move in the same direction as the wave travels. The same direction as the wave travels. Like that, okay? Look right here. So if you think about if you have a slinky like they have right here, and you just stretching the slinky out like this, that's a longitudinal wave right there, because the energy is, regardless, longitudinal and transverse waves, the energy is still traveling in the same direction, but it's just all about how they affect the particles, the particle motion. Okay, so just the opposite with a transverse wave. Transverse wave moves the particles in the direction that is perpendicular or 90 degrees to the direction that the wave propagates. So look how, even though my wave right here is traveling from left to right, you see our slinky is moving up and down 90 degrees from the beam. Okay, that's how transverse wave. That's our description of a transverse wave and how it affects particles. So when you think about transverse and longitudinal waves, it's all about how they affect the particles in the medium. Longitudinal waves, particles are moving parallel to the beam, or parallel to the sound. Transverse wave, they're moving at perpendicular to the sound, or 90 degrees. Okay, and we'll get there. That's your concentration base. That's your concentration base. Okay, so here goes the image of how that works right there. So notice that how transverse waves, they're both traveling in the same direction, correct? But transverse waves, they're moving the slinky up and down, up and down. Remember I was talking about your battle ropes when you're in the gym, and even though all my energy is going forward, when I'm hitting the battle ropes like this, my rope is moving up and down to make that energy travel this way. Okay, that would be an example of a transverse wave. Okay, in a longitudinal wave, see our energy, our particles are moving back and forth, are traveling along the same direction that the energy is going. Okay, go.
What is the arrow pointing?
Which way?
Back to the.
Because remember, sound causes the cavitation of the particles in the body. So they're not just going to be going this way, because they have to come back to their original place, right? So that's why it's going to cause them to vibrate back and forth. It's going to cause them to vibrate back and forth.
This has nothing to do with the position of the transducer, does it?
No. When we talk about longitude and transverse wave, it's all about particle motion, how they affect a medium, how they affect the particles in the medium. Okay, just like another type of wave would be a surface wave. A surface wave would be like waves in the ocean. Think about waves in the ocean. They're at the top, they're rolling. But when you're deep in the ocean, you don't have waves on the bottom, right? So those are called surface waves. There's waves that separate two different surfaces. Okay, those are different. I'm just giving you an example. You don't have to know what a surface wave is. I just want you to know what transverse and longitudinal waves are. Okay. So, tell me about transverse waves.
Transverse is
They go up and down like what? Perpendicular. I want that to be the key word of how they affect particle motion.
perpendicular to what?
Perpendicular to the energy transport, or to the direction of the beam. Okay, the direction of that sound wave. Okay, they go or 90 degrees. So if my sound is traveling towards Dewey, if it's a transverse wave, it's going to affect particles like this, up and down.
I understand that part. I just wanted to understand to what.
Oh, yeah, the energy or the direction of the sound wave. Direction of the sound wave. So just the opposite. Longitudinal waves are parallel to the direction of energy transport, because that's what waves do, transport energy, right? Energy transport, the direction of the wave, both of them mean the same thing. Okay? We're good, guys? All right. So let's talk about in phase and out of phase waves. So we're talking about waves being in phase and out of phase, we need more than one wave, right? We need at least two waves when we're talking about waves that are in phase and waves that are out of phase. When we talk about waves that are in phase, we're saying that their peaks is the maximum the wave goes up. Remember we were talking about a graph the other day? So if we just drew a line straight through this would be the peak of this wave right here, right? This would be the trough of this wave, the lowest point. The peak is the highest value, the trough is the lowest value, okay? So when you have two waves that are in phase, their peaks and their troughs are gonna travel at the same time. Their peaks are gonna be met at the same time, and then their troughs are gonna occur at the same time, okay? That's what in phase is, okay? So out of phase waves, they're just the opposite, okay? Out of phase waves also meaning, I'm sorry, I misspoke. In phase also can be stated as in step. Out of phase can also be out of step, okay? Out of step happens when the peaks and troughs occur at different times. So these two waves right here, these are perfectly out of phase, right? They're perfectly out of step waves, okay? So if I drew a wave like this, then I had another wave with my black marker. So I'm gonna not draw it so it's perfectly out of phase. That's not a good example. That's not a good example.
HIT wave.
I'll start up and you start down.
Come on. That's not a good example at all right there. Let me do one. Boom. Okay.
Let's be at the same.
No, you didn't do it right either.
I thought you were trying to do, what you trying to do it?
I'm not trying to do them perfectly out of phase. I'm trying to show that even if it's a little shifted, if they're not, see how this peak is exactly the same as this trough.
Right.
Even if they're a little slid over, they don't have to be perfectly out of phase for it to be out of phase is what I'm saying. I don't know why I can't do it. I just want to draw perfectly in phase and out of phase.
No.
See, it's tough. It's tough to draw, but I do have an image coming up about that. So remember, guys, in phase waves are when two or more waves, their peaks and troughs occur at the exact same time. Okay, out of phase or out of step when they occur on different times.
So the in phase, let's say the top line is shifted, but
Shifted away.
to the left.
Then that's out of phase. So the peaks and valleys also mean in troughs. The peaks and valleys don't occur at the same time. So if that blue was just shifted over just a little bit, that's what I was trying to represent right here, but I couldn't draw it for some reason. I don't know what's wrong with it.
Okay, so the bottom one is like the top of the blue line was shifted maybe like a little bit to the right or to the
It
left.
still will be out of phase.
Yeah.
It will still be out of phase. It will still be out of phase. This is a completely out of phase wave. A completely out of phase wave or out of step wave. Okay? So let's talk about interference, guys. Interference occurs when multiple sound beams arrive at the same identical location at the exact same time, and it is going to cause these waves to interfere with one another. The waves will lose their individual characteristics and form one single wave. Okay? So, for instance, these two waves, you see how they meet right there? That's interference right there. That's going to cause these two waves to have some type of interference. Okay? And we're going to talk about, because that's a perfectly out of phase wave, we're going to talk about what happens when two waves are perfectly out of phase. All right? So, we have two types of interference: constructive interference and destructive interference. Guys, write this down. In phase waves only produce constructive interference. Out of phase waves, because I know you guys have a question in the book about this. Out of phase waves will always, when these waves meet, will always be destructive interference if they're out of phase. Okay? In phase will always be constructive. Out of phase or out of step will always be destructive when they interfere with one another. Okay? So constructive interference, it occurs when a pair of in phase waves and it results in the formation of one single wave. Remember, when these two waves combine, when they meet at that same location at the same time, they're gonna lose their individual characteristics and form one wave. Okay, so when they're constructive interference, those the resulting wave is going to be of greater amplitude than either of its components. Okay, and just the opposite for destructive. So remember, destructive interference only occurs when waves are out of phase or out of step, and when those two out of phase waves interfere or meet at the same location at the same time, the resulting wave is going to be of lesser amplitude or of lesser energy, less intensity than the wave that formed it. Okay? Here we go right here, guys. So here we have, look at these waves. You see how they have different intensities or different amplitudes? Amplitudes meaning amplitude, power, intensity. What we heard those? What are those? Those are all acoustic parameters.